Thus far, the controllers we've been looking at are feedback controllers. In this class, or in this video lecture, we'll be looking at feed-forward control, which is basically an open-loop controller that we will put in front of our closed-loop plant. So we're first of all going to be looking at why do we need to move beyond feedback controllers, and then formulate this feed-forward controller and look at the benefits and limitations of it. So first of all, feedback control. It has a lot of benefits. It requires very little knowledge about the plant. We can have a poor plant model and still design a pretty darn good feedback controller that makes the system respond the way we want it to. It's also field tunable, meaning that we can tweak it in the field, and as the plant changes, we can use some Ziegler-Nichols methods to tune the gains of the controller. It's also very easy and fast to implement. Now, with all of those benefits, why don't we just stick with it? Well, you've noticed that there are some performance limitations. So we've been doing some analysis of what's the steady state error, and we find that we do have steady state error for a variety of signals. So how could we improve the performance? Well, this says let's move to possibly a different type of a controller. Now, what are some of these limitations? Well, let's look at this as a fairly simple system. It happens to be what you're looking at in your lab, where you just have an integrator K over S for your plant and just a proportional controller right now. And we have this for our closed loop transfer function, A over S plus A. And when we generate a Bode plot of this, we remember that we've got these roll-off frequencies, or these corner frequencies, where whenever we're going to be crossing this minus 45 degrees or getting to this minus 3 dB point, we call that our corner frequency, and above those frequencies we really don't want to be operating. We don't have very good performance. Well, how do we improve the performance of our system at those higher frequencies? Well, this is where we need a different type of controller. So we can't track these high frequencies. What we're going to do is we're going to add an open loop controller, which is now based on knowledge of our plant. So with that feedback controller, we didn't need to know very much about our plant. We're now actually going to design a controller where we need a great model of our plant. So this is called a feed-forward controller. This is basically an open-loop controller. There are two main types. The first is what we refer to as a disturbance feed-forward controller, and this is where we're measuring a disturbance. So imagine that we're controlling the temperature or the humidity in a room. Well, one way to do it is just to respond to the temperature that's already in the room with a standard thermostat, but a more intelligent way to be doing this would be to perhaps measure the outside temperature, or maybe also measure the outside wind speed, and then use a very complex model of the building dynamics, in other words, how well does heat transfer through the walls, to predict or improve our controller. So that would be a disturbance feed forward, where we need to add an extra measurement device to the disturbance. Now, another type where we don't need to add another sensor is a reference feed forward system, and this is what we will be looking at here, and this is also called a second degree of freedom controller. So what does this look like? Well, we take our closed loop system that we already have, so we still want to keep a closed loop system, and you'll notice that I've now labeled my reference function as R2. Now the reason for that is I'm going to take this old closed loop plant, and now I'm going to stick a feed forward controller, basically another controller, in front of this. So I'll have two controllers, my feedback and my feed forward. Now the objective of this is I want to design my feed forward controller to have perfect tracking, regardless of what my reference is that I'm trying to track. So how do I do this? Well, I can say the output Y of S divided by the input R of S is the input to the entire system. This is just going to be the feed forward controller multiplied by the closed loop controller, and to have perfect tracking, I want this to be equal to 1. So it doesn't take me long to start looking at this and saying, well, with a closed loop controller that has a certain form, I just want the feed forward to be the inverse of that. I multiply them together and I get 1. And that's exactly what we're going to try to do here. So I have the closed loop system of A over S plus A, and I'm now going to force my feed forward controller to be S plus A over A. I multiply those together and I get 1, or perfect tracking ideally. Now, let's take a look at how this actually behaves from a frequency response. So we already looked at the Bode plot for the closed loop transfer function, or the closed loop plant. Now, let me do the same thing for this feed forward controller. I get the magnitude and the phase angle of this, and you'll notice that my Bode plot really just looks like the flip of what I just had before. Remember, I was dropping off as my frequency increased. Here, we're increasing the gain as the frequency increases. And you'll notice that my phase now we're getting a leading phase angle which approaches 90 degrees as we get to high values. So I multiply these together and I should just get horizontal lines for both the magnitude and for the phase angle of 0. That would be ideal. Now, what are some challenges or problems with feed-forward control? The first is that it will demand, especially at higher frequencies, it will demand extremely high inputs or outputs from our actuator. And often this will saturate the physical system. So we're left with the fact that physical systems can only manage a certain amount of power. So if I have a cruise controller for my car and I demand that I go from 50 miles an hour to 70 miles per hour right now, I'm going to saturate my actuator. In other words, I'm going to saturate or give full throttle response to my engine, and it won't be able to instantaneously change that. So that's just inherent with physical systems. Model uncertainty. You notice that I have to have a perfect plant model here. And very often we don't have a very good idea of what our plant model is, or our plant model would change over time. So as perhaps for our system, as the oil gets warm or as friction increases or something like that, our model will change of the system. And because we've designed our feed-forward controller around a given plant, if that plant changes, now we have issues, and this open-loop controller can't quite do it. And that is why we always connect this with a feedback controller as well. So we don't ever just use this open loop control. We always want to add feedback control as well to manage those slight errors that build up due to the model uncertainty. Now the other thing is you'll notice that I am creating gains here at higher and higher frequencies. So what's happening is I am basically magnifying any noise that I have in my system. And often the noise from fluorescent lights and things like this is fairly high frequency compared to the mechanical systems we're dealing with. And so we're amplifying that noise, and then our controller is responding to that noise. We don't want that to happen. So one option here is we can add a pole. And the idea with adding a pole is I basically want this to ramp up for a while, and then I want it to trail off and flatten out. And that's what a pole will do, is adding and minimizing the amplification of that high frequency noise while still getting the benefits that we want. Now the last one is more from a mathematics standpoint, where by creating this feed-forward controller, we have created what we call an improper transfer function. So a proper transfer function simply has the degree of the denominator needs to be greater than or equal to the degree of the numerator. And in the system that I have just proposed here with this feed-forward controller, we have a degree of 1 of our numerator and degree 0 of our denominator. So this would be an improper transfer function. So this is for a proper transfer function, and then we say for a strictly proper, the degree of the numerator always has to be greater than the degree of the denominator. I'm sorry, than the degree of the numerator. So denominator has to be greater than the numerator. So this is also solved by adding a pole. So let's look at how we add that pole. What we're going to want to do is add what we call a fast pole, meaning a pole that has a value that is higher than the highest natural frequency where we want to be operating, or the highest frequency we want to be running our system. Certainly much greater than A of our original system. That's the objective. So now our feed-forward controller has that same S plus A over A term, and what I'm adding here is this B over S plus B. So this is now my feed-forward system, and you can see from the Bode plot, I get the increasing magnitude that I want, or the gain that I'm applying through those kind of that mid-range frequency, but then I'm rolling this off and flattening it out at higher frequencies so I don't amplify that high frequency noise. And similarly, I'm getting this phase angle plot that I want. So what happens when we put all this system together? Well, here is the full transfer function of the system. So you'll notice that I started off with a closed loop transfer function that was A over S plus A. And once I multiply this out, I end up with a transfer function that is of the exact same form. And you say, well, why is this any better? The reason it's better is because these values of B are much greater than the values of A. So we have extended the range that our system is able to operate at, and basically be able to now run at higher frequencies and have much better tracking up to higher frequencies, and just simply shifting everything to the right. So we get a much better operation of our system by adding this open loop controller in front of our feedback controller, creating this feed-forward system.